Hello. Today we are going to talk about FPGAs in machine learning and quantum computing. Team members are Giorgi, Tsartside, and Shota, Sisvelashvili, and Giorgi will talk about FPGAs in quantum computing later. And in my part, I'm going to discuss the usage of FPGAs in machine learning. So let's dive in. What is FPGA? The FPGA is a field programmable gate array. It is a hardware circuit with reprogrammable logic gates, and it enables us to create custom circuit while the chip is deployed in the field by overriding the chip configuration. This is different from regular chip, which are fully baked, and we cannot reprogram or change it. With FPGA chip, we can create everything from simple single function logic gates to multi-core processors. Common uses for FPGAs include space exploration, defense system, telecommunications, image processing, high performance computing, and the networking. But the next thing I want to talk about is FPGA for machine learning. And in this part, mainly I'm going to focus on why it's better or not better to use FPGA instead of GPU and vice versa. When we deciding to use one of them between GPUs and FPGAs, we need to understand how to compare two of them. So there are some differences between GPUs and FPGAs for machine learning and deep learning as well. The first thing I want to talk about is compute power. FPGAs can produce roughly the same or greater compute power as comparable usual GPUs. FPGAs also have better on-chip memory, resulting in higher computing capability, and also it reduces the cost power required for high memory bandwidth solutions. Also, I would like to discuss efficiency and power. FPGAs can perform almost 10 times better than GPUs in terms of power consumption. The reason is that the GPU require complex compute resources, and it enables software programmability, which consumes more power. The next thing is functional safety. GPUs were designed for high performance computing systems. Graphic workloads, safety concerns were not relevant. However, GPUs have been used in applications, for example, in ADAS, where function safety is a concern. In that cases, GPUs must be designed to meet the safety requirements, which can be time consuming for vendors. So let's talk about pros and cons of using FPGA in a deep learning. Let's start with pros. The first one is flexibility. The reprogrammability is the greatest benefit of FPGA for deep learning and machine learning. machine learning. It can add significant flexibility to operations, and we can program individual blocks of our entire circuit to fit the requirements of the particular algorithm. Also, we can also modify it as needed if the programming does not fit as well as we expected. The next thing is parallelism. We can switch between programs to adapt changing workflows with an FPGA. We can also handle multiple workloads without sacrificing performance, and which enables us and allows us to work on the different stages of tasks concurrently, which we cannot do, by the way, with GPUs. The next thing is decreased latency. A larger memory bandwidth results in a lower latency than GPUs. It enables us to process significant amount of data in a real time, including streaming data. Additionally, FPGAs can provide extremely precise timing and reliability without sacrificing the flexibility. And the last thing about the pros is efficiency, energy efficiency. Lower power requirements for FPGAs, we can help reduce overall power consumption for machine learning and deep learning as well. This can be reduced. All of this can reduce overall cost of training and potentially extend the life of the equipment. So after speaking about the pros, we should consider that there are the cons as well that we need to explain and discuss. The first one is programming. It's kind of weird, but programming is one of the cons of the FPGA, because programming FPGA circuits requires significant expertise, and that is not easy to obtain. The next thing is implementation complexity. Implementing FPGAs for deep learning or machine learning is relatively untested and maybe might be too risky for some organizations. Lack of support and minimal community knowledge means that FPGA are not yet widely accessible for deep learning applications or machine learning applications. The other con is expense. The cost of the FPGA themselves in a combination with implementation and programming cost make the circuit a considerable investment. This technology is currently ill-suited, let's say, for smaller projects, and requires the investment given to comparably larger and ongoing implementations. And the last thing about the cons I want to talk about is lack of libraries. Currently, there are only a few, and if any, deep learning libraries that can support FPGA without our modification. However, I'll bet there is a project that researches from the University of Columbia, University of British Columbia. They are working now the special research called VFlow. This project is attempting to create compatibility between FPGAs and deep learning software called TensorFlow. So that's all. That was all about the using FPGAs in deep learning and the machine learning. Now, Giorgi will talk about using FPGAs in quantum computing.
Okay, let's discuss about FPGAs in quantum computing. As time goes on, we realize that the classical computing has met its physical barrier and cannot be upgraded further. That is why engineers and scientists have started working on quantum computers, which would significantly boost the computing power. At this moment, quantum hardware is a very challenging problem, and creating it costs millions of dollars, still with significant errors. That is why we need an emulator or classical computer to play around and accelerate quantum software development, which in turn might offer us some service solutions. There are just two ways of emulation, software and hardware by FPGA. And studies shown that FPGA emulation is much way better than software emulation. Now let's briefly discuss the fundamentals of quantum computing. As we know, quantum computers operate on quantum bits or qubits. Qubits have two computational base statements denoted that bra0 and bra1. Unlike classical bits, quantum bits might be either 0 or 1 or any value in between. So there are some quantum gates, for instance, Hadamard gate, phase shift gate, X gate, CNOT gate, and Z gate. Explaining them is not important right now. We maybe just move on to the next slide. So when we have gates and when we have qubits, the very fundamental of quantum computing is to somehow entangle those qubits using quantum gates. And sometimes this entanglement process requires considerably more resources than a gate where no entanglement occurs. This is the reason why efficient simulation of quantum computing is difficult on classical computing devices. Now let's consider two input CNOT gate and the situation where controlled qubit is in superposition. In such case, the operation is described as follows. So we have two operator. One is control, one is target, and we see the algorithm of operation. In integral state, two qubits cannot be represented individually. For this case, two qubits, C1 and C2, they are written separated because they aren't entangled. But if they are entangled, they are denoted and unified under one pronotation. And once they are entangled, they cannot be separated any longer. So let's consider the situation when we have an CNOT gate, and for n input CNOT gate, the number of complex multiplications is 2 to the power of n. And you may agree that this exponential increase becomes a serious, very serious issue and problem with entangled system. FPGAs have a large amount of logic cells, and multiple FPGAs can be combined for even bigger circuits, and therefore large circuits with entangled states can be emulated. I think the entanglement poses a fundamental bottleneck in modeling quantum systems by classical means. So to finally compare, the hardware emulation of quantum circuits has significant advantages over software simulations. The first, the evolution of each quantum bit can occur in parallel, and software simulations has a sequential pattern, sequential simulation. the emulation evolution of each quantum bit. Efforts are being made to create parallel software simulations, but they cannot achieve the parallelism available through emulating the quantum circuits using FPGA. For the future works, the emulator is also scalable and has the great potential of emulating complex quantum circuits. This emulation can also incorporate further quantum computing concepts like quantum error correction or fault-tolerant quantum computing or quantum measurement techniques. And this would be especially helpful in developing quantum practices for quantum computer. So this is the end of our presentation. In today's presentation, we discussed FPGA in machine learning and the role of FPGA in quantum computing. I hope you enjoyed this presentation. Thank you for your time and attention.